We have done an econometric analysis and the topic we have chosen is fertility rate. We have studied data from 80 different countries from all over the world. Then we will analyze which variables may have an impact on the average number of children per woman through developing a constant slope model as well as a constant elasticity model. The last step will be the interpretation of the results.
We are going to start with the constant slope model. According to the data we obtained through online research, we could design the following scatter plots graphs, which will show the relations between the number of babies per woman with each of the independent variables we have selected. On the one hand, we see that there are 3 scatter plots in which the independent variables are positively correlated with the dependent one. On the other hand, we observe that most of the scatter plots have a negative correlation. With respect to a dummy variable, we know that this is a mutually exclusive variable, that means presence or absence. Regarding the shape, we see that it will not have influence on the final model.
We apply the linear estimation and we get the initial model. We establish a null hypothesis of all variables being equal to 0. Then we compute the if test, and as the p-value is below 0.05, we can reject only hypothesis and accept that all variables are valid for our model.
I'm going to explain the elimination of variables. We establish a null hypothesis assuming that variables equal to 0. Once we have calculated the t-test, we accept the null hypothesis when p-value is higher than 0.05. If more than one variable equal to 0, then we reject the one with the highest p-value, in this case b10. Then we remake the model and eliminate the variables one by one, until we keep only the parameters with a p-value below 0.05, rejecting now the null hypothesis.
We're going to analyze our final model: coefficients p0, constant coefficients p1, fetal mortality, and p2, maternal mortality. Now we have the coefficient of determination r², which indicates how good our model is. In the final model, it has decreased, however we think it's a good result, because it is very close to 1. Standard error provides the absolute measure of typical distance that the data points fall from the regression line. With the elimination of variables, we reach a smaller standard error. Sigma refers to the standard deviation of the errors. It increases with the elimination of variables. Degrees of freedom, number of data minus number of parameters, increase too with the elimination of variables. The quadratic error is the sum of the residuals squared. It indicates the accuracy of the model. As smaller the quadratic error, more accuracy. So, in our case, we have less accuracy with the elimination of variables.
In this section, we have calculated the residuals, and here you can see some of them. In the graphical representation, we can see that the model presents heteroserasticity. This is, as bigger the dependent variable, bigger is sigma. Therefore, it would be dangerous to us to use this model in decision-making. Secondly, we have calculated the confidence interval. There are 4 residuals that don't fit in the interval. We call these countries outliers. Moreover, we have done the same procedure with 3 countries that were not represented in the model: Somalia, Syria, and Vietnam. We have calculated the lowest and highest values by subtracting and adding the confidence interval to the estimate, and we see that the real values fit between these values.
We begin with the constant elasticity model. Here we have transformed our variables into logarithms in order to stabilize the variables which are more skewed, easing our work. First we have the positively correlated variables, same as the other model, and then equal for the negative ones, followed by our dummy variable, here with the same shape, making us believe it would influence the model, but it turned out to affect it.
We apply the linear estimation, we get the initial model, then we compute the if test, and with the result, we can assume that total variables are valid for our model.
In this case, after establishing the null hypothesis, we calculate the t-test, and we observe that the highest p-value corresponds to p7, so we remove that variable and remake the model. Here we reject the null hypothesis since every p-value is below 0.05, which proves that our variables affect the model.
Now we're going to analyze our final model. Coefficients. We keep the parameters. Some of them will impact positively and others negatively in our model. R² is very close to 1, so it indicates our model is actually quite good. As you have only removed one variable, the standard error reduction is very small, and the degrees of freedom increase only by 1 unit. Finally, sigma stays the same with a small value, as well as quadratic error, which indicates that our model is quite accurate.
After the calculation of the residuals, the representation tells us that the heteroserasticity problem has been solved. Here we have the confidence interval, and there are also 4 outliers.
In order to compare the models, we have eliminated the logarithm by applying this equation, so now we have the same dependent variable. We conclude that the results of the residuals estimation are very similar in both models. However, the scattered plots in the residuals of the elasticity model seem to be more independent, identically distributed. Finally, both models have good and bad properties, so we cannot determine that one is better than the other, but we have worked and understood better the elasticity model.